Hello everyone. In our last video, we introduced the concept of logarithms and logarithmic functions. So in this video, we'd like to go ahead and explore that a bit further and learn the properties of logarithms. So of course, we learned that the logarithmic function is defined by f of x equals log base p of x with these restrictions on the base. Base has to be positive and not 1, and also we had an extra requirement that the argument of the logarithm, here known as x, in this case should be positive as well. So the main relationship that defined logarithms for us was this biconditional, that y equals log base p of x if and only if x equals b to the y. Now, we already know about three fundamental properties for exponents, which is the product rule, the quotient rule, and the power rule. We're going to learn in this video that these three rules also have logarithmic counterparts. After all, recall that logarithms are just exponents, so it makes sense that they should have laws similar to the laws of exponents. And that's what we're going to look at today. All right, the first property we're going to introduce is going to be the product rule for logarithms. And because it is very empowering to be able to not just know something, but really understand it and be able to prove it, we're going to go ahead and prove these rules as we encounter them. So let's go ahead and take a look at how we would maybe prove a rule like this. So we'll go ahead and give these two expressions on the right side here some names. So let's go ahead and let log base b of m be x, and let's let log base b of n be y. We're just giving it any names. You could have called them u and v, your favorite letters, doesn't matter. The game plan is we're going to start with these logarithmic forms. We're going to go to exponential form, take care of some business with the product, and then we'll go back to logarithmic form. So that's where we're headed. All right, so if we go ahead and put both of these in exponential form, we get m equals b to the x and n equals b to the y. That's just a quick application of what the definition of logarithms tells us. Now, since I'm going to be proving something about the log of a product, it's good for me to know what that product looks like. So now we're going to go ahead and multiply m and n. So we get m times n equals b to the x times b to the y. Now, if I just go ahead and use the laws of exponents, this screen is acting a little funny. Okay, here we go. So if we go ahead and apply the laws of exponents, we get m n equals b to the, we're going to use the product rule here to give us b to the x plus y. All right, we've pretty much accomplished whatever we wanted to accomplish using the exponential form. Now we're ready to go ahead and go back to logarithmic form. So we're going to take this equation and we're going to put it in logarithmic form. So we end up with, this implies log base b of, remember you put the entire exponent on this side because that's going to be the logarithm, and the power, which is mn, will become the argument here. Now we can use parentheses so that there is no confusion. And now all we're going to do is we're going to substitute you remember what x was? X was log base b of m. And if you recall, y is just log base b of n. And that's exactly what we were trying to prove. We were trying to prove that log base b of mn equals log base b of m plus log base b of n. So it's a very nice simple proof, but it's very indicative of how we approach proofs in mathematics. So make sure that you understand it before we move on to prove the quotient rule. We're going to use exactly the same approach for the quotient rule, which basically says the log of a quotient is the difference of the logs. If we go back to our previous screen, the mnemonic for this, the way you want to remember this, is that the log of a product is the sum of the logs. Okay, so be very careful. Log of m times n is not log of m times log of n. It's the log of m plus log of n. Of course, similar to the rule we had with the exponents too. When you multiply two powers with the same base, you kept the base and you added the exponents, remember? And of course, logs are exponents too, so it's not surprising that they behave in a similar fashion. All right, so we'll use the same game plan. We'll go ahead and give these two items on the right a name. So let's go ahead and let log base b of m be x again, and log base b of n be y. So we'll go ahead and put both of those in exponential form. So we get, this implies m equals b to the x and n equals b to the y. So now this time we're interested in the log of a quotient, so we want to know what the quotient m over n looks like. So this time we'll go ahead and see what m over n becomes. Well, of course, that's going to become b to the x over b to the y. Now, if we apply the quotient rule to that, we get m over n equals b to the x minus y. And basically, our use of the exponential form has been exhausted, so we go ahead and put this back into logarithmic form now. So we get log base b of m over n equals x minus y. Now, if we substitute log base b of m for x and log base b of n for y, we end up with log base b of m minus log base b of n. And we have just proven what we wanted to prove. So QED. All right, so two nice proofs. Make sure you actually can carry them out on your own. That's fantastic experience with math and with logic. And then we'll go and prove the power rule, which is the last one that we're going to look at. So the power rule states that if you have the log of a power, it's going to be the exponent times the log. Now, this power rule is going to be a particularly important rule for us. They're all three are important, but this is extremely unique because we've never seen any rule until now that takes an exponent and makes it something other than an exponent, in this case a factor. So this rule is going to be extremely powerful and extremely helpful for us when it comes to solving very difficult exponential equations that cannot be solved in the method that we've been using by making both sides powers with the same base. Those are going to require the utilization of this rule in particular. So the proof runs similar. It's in some ways simpler because there's only one log we're dealing with. So we're going to go ahead and do the same thing. We're going to let log base b of m be x. You should definitely see if you can carry this proof on your own, because that would be a fantastic way of gaining some confidence if you can manage that, because I think you'll be able to do it if you understood the previous two proofs. All right, so now we go ahead and write this in exponential form. So we get m equals b to the x. Notice this time we want to know what m to the n is. So we're going to go ahead and raise both sides to the power of n, and we get this like so. So if I just simplify the right side, I get m to the n equals b to the xn, or I'm going to write nx, you'll see in a minute why. So now let's go ahead and take this equation and put it in logarithmic form. So we get log base b of m to the n equals nx. Now all you have to do is remember what x is. Remember, log base b of m. So we get n times log base b of m. Isn't that what we were trying to prove? That the log of a power is the exponent times the log. And that's exactly what we accomplished. So notice how the game plan was the same for all of them. We start with logarithmic form, go to a simpler form we're familiar with and we know the rules of, do what we need to do, and then get back to logarithmic form to end the proof. And that's basically all three rules that we're going to be using. We'll look at a summary in a second. Okay, so here we see a summary of the rules that we just proved. The product rule, which of course told us the log of a product is the sum of the logs. The quotient rule, which states that the log of a quotient is the difference of the logs. And the power rule that tells us the log of a power is going to be the exponent times the log. These are extremely important rules. Just like with the laws of exponents, we're going to be using them extensively in the next few sets. So make sure you have these completely down. Now let's go ahead and apply the properties we just proved to a few actual examples. All right, here on the left, we have the log of this product. We're going to be applying the product rule a few times first to get comfortable with that one. And remember, the log of a product is the sum of the two logs, the two basically logs of the two factors. So here we're going to go ahead and break this down as log base 10 of 2 plus log base 10 of 100. Now log base 10 of 2 is not a simple number because we don't know what power of 10 gives us 2, but log base 10 of 100 is a nice simple number. Remember that invisible number you have to imagine here. 10 to what power gives 100? That's 2. So we go ahead and say that's equal to log base 10 of 2. We don't do anything with that one. But the next one we can just simply write as 2 because that's what log base 10 of 100 is. It's 2. All right, this next one we can go ahead and split that up as log base 7 of 49 plus log base 7 of x. Now log base 7 of 49 we know is 2. What power of 7 gives us 49? The second power, and plus that one, the next one we just write and leave as is. The next one, we're going to apply the product rule twice. So the first time we can, for example, apply it to u and then vw, and then we apply it again. So we end up with log base b of u plus log base b of u vw. So we split it up kind of like this right now. And now we notice we can apply the rule again to this log of a product. So we end up with log base b of u plus log base b of v plus log base b of w. Now normally we don't show this step. We understand this, and then from this point forward, when we see that, we know that that's just going to be the sum of each log, the log of each factor anyway. So normally we jump from this to this outcome and we bypass that step. Okay? All right, so let's move on to a few more examples. Remember that in mathematics, whenever you learn a formula or any kind of a equation, you have to be comfortable with it from the going from left to the right and backwards from right to left. So now we're going to go in this direction from right to left. We're given a sum, and we're going to write it as the log of a product. So, and if we can, we'll simplify thereafter if possible. So here we notice that we can write this as log base 10 of 2 times 50, which is log base 10 of 100, which of course does become a nice simple 2. What power of 10 is 100? We know that's just 2. So that's the final answer there. So for the next one, we're going to take that and we're going to write it as log base 5 of basically just the product, like that. And that's all we can do there. So sometimes people use parentheses on something like that, and sometimes they don't. We'll go ahead and use it. It's a little bit safer. All right. So here, of course, this 7 is going to play the role of m, and this entire factor, not part of it, but the entire factor is going to play the role of n. So we're going to get log base 2 of 7 times x minus 3. Now the only other thing we can do is just go ahead and distribute that. Here you must use parentheses. So we get 7x minus 21. The reason for the must is because if you write log base 2 of 7x minus 21 without parentheses, others will assume that you have to take this log and then subtract 21, which is not what you want to be interpreted. So make sure that you use parentheses on that one. Okay, let's go ahead and apply the quotient rule a few times. So we know that the log of a quotient is the difference of the logs. So for this first one, we're going to get log base 10 of 79 minus log base 10 of 100. So log base 10 of 79 is not a nice simple answer. We just leave it as is. But this one we know is 2. Like so. The next one, we're just going to get log base 4 of m minus log base 4 of n, and there's nothing else we can do. For the next one, we're going to get log base b of 1 minus log base b of b. Both of those should look familiar to you. What power of any positive number is 1? You guessed it. 0. And minus what power of a number is itself? You guessed that too. 1. So the final answer will actually be -1, like so. All right. So make sure you're comfortable with these and then we'll proceed. All right, as we did with the product rule, we're going to now go from the right to left direction. So we're given a difference of two logs and we're going to write it as a log of a quotient. So here we're going to get log base 10 of 3,000 over 3. We know that that's log base 10 of 1,000, and I think you'll be able to answer that, right? What is log base 10 of 1,000? What power of 10 gives us 1,000? In other words, what exponent do we need? You said it. Oops, here we go again with this business. All right, I managed to tame the wild whiteboard again. All right, so we know that 10 to the power of course, 3 is 1,000. So the answer is 3, and that's all it is. All right, for the next one, we're just going to get log base 5 of x over y. This is just to give us some practice with the rule. Here, of course, 7x is playing the role of m. The entire expression y minus z squared is playing the role of n. So we're going to get log base 2 of 7x over y minus z squared. Now let's go ahead and take a look at a few problems involving the power rule, which of course states that the log of a power is the exponent times the log. Remember, it's an extremely important rule because it's the only rule we have in mathematics that takes an exponent and turns it into a factor, thereby releasing it from its imprisonment in that exponent position. All right, so if we go ahead and take a look at these, we're going from basically from left to right. We have the log of a power and we're going to turn it into this product here. So the first one is going to become 4 times the log base 3 of 5, and there's not much else we can do because log base 3 of 5 is not a very basic simple number. All right, for the next one we have log base 8, and you may wonder why that's even here, because of course, as you know, we can write a radical as a fractional power. So we can go ahead and write that as 64 to the power of 1/3, and this in turn we can simplify using the power rule, because now we know that we can bring the 1/3 over here and turn it into a factor. So we get 1/3 times log base 8 of 64. Now we know what log base 8 of 64 is, because we know 8 to the power of 2 gives 64. So log base 8 of 64 is 2. So times 2, so the final answer we'll write as 2/3. Now here we're going to go ahead and just bring the 6 down, and we get log base b of quantity, parentheses are mandatory here, just like that, and we're done. There's nothing else we can do. Remember, we never did a log of a sum rule, did we? And that's because it doesn't exist. So don't do anything after that. You are finished. This is not log base b of m plus log base b of n, okay? So make sure you don't make that mistake. Just leave it as is. All right, as is common to what we have been doing, now we're going to go from right to left. So we're given some products, we're going to write those as powers, log of powers. So this becomes log base 2 of 7 squared, so we just basically get log base 2 of 49, and that's all we can do there. The next one, we're going to get log base 5 of x to the -3, which we can of course write as log base 5 of 1 over x cubed, like so. On the next one, we're going to write log base b of u to the 1/4. If a problem demands it, you can of course always write that as log base b of the 4th root of u, and that would be correct as well. All right, so there's some practice with these rules. Now, if you recall, these two rules we also looked at in our previous video. You know that log base p of b to the x is x, and b to the power of log base p of x is also x. So if we apply these, we end up with, for example, in this one, notice the role of b is being played by 10. Since the base here and the base of that power are the same, we're just going to get 20. On this one, we have to do a little bit of work first. So we have to take the 8th root of 5 and first write it as 5 to the power of 1/8. Now we can see we're exactly in this format, and we're going to just get 1/8. Here we have 9 to the power of log base 9 of CD. We're in this format. As long as this base here and that base are the same, we're just going to get the argument. So we're just going to get CD. That's all. Same here in this next one. As long as these two are the same, the base here and the base of the log, we're just going to get whatever that argument is. So here we're just going to get square root of x. All right, so the last thing we're going to do now is to combine all these logs in the same problem. So first we'll just review them. Remember, these are all the rules of logs we've studied so far. We started with just the basic definition of logarithms, which you should be familiar with by now. Then we did the product rule, the quotient rule, the power rule, the log of 1 rule, the log base p of b rule, the log base p of b to the x rule, and the b to the log base p of x rule. So these are the inverse rules basically, and we're going to be utilizing some or all of these in the next few examples. All right, in this example, we want to write this log as a combination of single logarithms. So what do we mean by simple logarithms? We mean logarithms of where the argument is just either a constant to the power of 1 or a variable to the power of 1. That's what we mean by simple logs. You'll see in a minute what they look like. So the first thing we'll do, well, let me just go ahead and copy the problem down. So let's go ahead and first and foremost apply the product rule. So we get log base 5 of 5 plus log base 5 of x to the 5. Now, so here the property we used was the product rule, and of course we used it from left to right. Now we can go ahead and remember this basic rule, the log of base b of b equals 1, and log base 5 of x to the 5, what we can do is we can bring the 5 down, so we get 5 times log base 5 of x. Now, Notice that is a simple argument because it's just a variable to the power of 1. And there's really not much else we can do. So here at this point we are done, and the property we used here was the power rule, also used from left to right. And that will be the final answer of the rewriting of that expression. Okay, so next we're going to take a look at this problem, and the first thing we'll go ahead and do is turn that radical into a power in this way. So we can say log base 8 of 8 over y to the power of 1/2. And here, of course, we're just using the radical to fractional exponent rule. And if you recall, that says the nth root of x to the m equals x to the m over n. And now we're going to go ahead and apply the power rule for logarithms, and this will give us 1/2 log base 8 of 8 over y. So the property used is the power rule, which of course says log base b of x to the n equals n times log base b of x. Next, we'll go ahead and apply the quotient rule, which says log base b of m over n equals log base b of m minus log base b of n. So here we will get, in parentheses, log base 8 of 8 minus log base 8 of y. We need the parentheses because the 1/2 needs to get distributed into the group. Okay, so make sure that you do use parentheses there, and that gives us, upon distribution, 1/2 log base 8 of 8 minus 1/2 log base 8 of y. Here we're just using the distributive property. And the last thing we want to do is go ahead and remember this rule, that if you have the log base b of b, that equals 1, for obvious reasons, right? Because b to what power gives you b? That would have to be 1. So we can replace log base 8 of 8 with just 1. So we get 1/2 times 1. This becomes 1. So that's just 1/2 minus 1/2 log base 8 of y. So there is the expanded version of this particular expression, written as a combination of simple logarithms, meaning logarithms with nothing other than just a simple variable, no powers or anything on it. All right, so make sure you can handle that, and then we'll proceed. All right, so here, obviously, if you look at it, the top level operation we're going to deal with here is a quotient. So we go ahead and use the quotient rule to write that as log base b of pq minus log base b of rs. And of course, we're using the fact that log base b of m over n equals log base b of m minus log base b of n. So now we notice that we have two products that we can deal with. So we have a log of a product here and a log of a product here. So the first one gives me the sum of the logs. So log base b of p plus log base b of q minus, I am going to need parentheses here. So the first thing that we did was we applied the quotient rule, and now we're applying the product rule. So we get minus log base b of r plus log base b of s, all within parentheses. Finally, we're just going to go ahead and distribute that negative. So we get minus log base b of r. Be careful where you locate that. It should be at the same level as the log, minus log, and we always want the base on there. So minus log base b of s. And that should do it. That's all we can do. Notice each of these logs is a simple log because their power is 1, just a variable or a constant to the power of 1. So here we just did some simplifying. So that's all there is to it. Okay, let's look at another one. All right. Of course, you know how when we go from this side to that side, now we're going to go the other way around. We always do that in math. So now we're going to take this combination of logs and turn it into a single logarithm. We're doing the exact opposite of what we just did in those few examples. So we'll start with 4 log base b of a minus 5 log base b of b. So obviously, if I'm going to try to get these into just one logarithm as a format, first I should go ahead and get rid of the 4 and the 5 and take them and make them powers using the power rule. So I get log base b of a to the 4 minus log base b of b to the 5. Notice since I kept the minus here, it doesn't go onto the exponent. If I wanted to do that, I would have written plus and then I would have put the minus there, but we don't need to do that. All right, so here we just applied the power rule, of course, going that way. And now we can go ahead and write that as the log of a quotient, because remember, a log of a quotient is the difference of the logs. So we get log base b of a to the 4 over b to the 5. And here we apply the quotient rule, of course, going in that direction once again. All right, so that's how you tame those beasts. All right, let's look at another. All right, so here again we have a combination of logarithmic expressions, and we're going to go ahead and combine them into just one log. So we'll go ahead and start by applying the power rule again. So we get the log base b of x to the 1/2 minus log base b of y to the 1/3. And here we just applied the power rule, so let's keep track of it. And now we're going to go ahead and apply the quotient rule since it's a difference. So we're going to get log base b of x to the 1/2 over y to the 1/3. There we just use the quotient rule. And finally, if we like, we could just go ahead and write those as radicals. So we can say log base b of square root of x over the cube root of y. There we're just using the nth root of x to the m equals x to the m over n rule. And that's all there is to that one. All right, here we're doing a couple of true or false questions we may encounter. So to handle a question like this, just go ahead and figure out what the left side is. Go ahead and figure out what the right side is. See if they're the same thing. So let's start with the left side. We have log base 3 of 27 over log base 3 of 9. So we know what log base 3 of 27 is. 3 to what power is 27? You said it, 3. And we know what log base 3 of 9 is. 3 to what power is 9? And the answer is 2. So that's what we have for the left-hand side. So if you want, you could put it like this. Then you can say the right-hand side is equal to log base 3 of 27 over 9. If we go ahead and divide 27 by 9, we get log base 3 of 3, which is, we know what is the power of 3 that gives 3? 1. So you notice they're not the same thing. So this is actually a false statement. And this is in order to, this is basically considered a counter example for this rule. So suppose somebody comes to you and says, hey, I just learned about logarithms. Did you know that the log base b of m over the log base b of n is equal to log base b of m over n? So instead of arguing with the person, all you have to do is show them this one example, and that proves that this statement is not true. So this really requires one of those lines through it, because they're not the same thing. So in order to prove a mathematical statement true, you have to do some work, like we did in the beginning of the video, proving the 3 rules of logarithms. But in order to prove something is not true, or that it's false or wrong, not a theorem or a true statement, all you have to do is show one example. So to prove that this is not a law of logarithms, we don't have to like sit here and write a full page of proof. No, all we need is one example, because the standard of truth in mathematics is extremely high. If you say something works, it has to work every single time. If it fails even once, we don't accept it as a rule. Let's look at the one on the right side now. So we'll start with the left-hand side, which is log base 2 of log base 3 of 9. Using the order of operations, we'll start from the inside. So we need to figure out log base 3 of 9. Of course, we know that's just 2. So this becomes log base 2 of 2, and we know that is just 1. So that's what the left-hand side gives us. The right-hand side is log base 11 of 121 over log base 12 of 144. Now we know log base 11 of 121 is just 2, because 11 squared is 121. And we know that log base 12 of 144 is also 2, because 12 squared is also 144. So this becomes 1. So here we can say this statement is true, because the left and the right hand side are indeed the same. All right, that was the last example we were going to look at. So I just wanted to close the video by warning you about these common errors, okay? Log of a product is not the product of the two logs. Log of a quotient is not the quotient of the two logs. The log of a power doesn't mean take the log and then raise it to the power. As you know, what it is you have to bring the exponent down and multiply it. The log of a sum is not the sum of the logs, and the log of a difference is not the difference of the logs. There are so many things that you can't do with logs. The best thing to do is just to learn the few things you can do, and then learn them well and apply them appropriately. All right, so I hope that helps out, and practice plentifully as always, and I'll see you in the next video. Be safe.